The universe through new eyes, introducing the James Webb Space Telescope. The cosmos is vast. For centuries we have looked up at the stars. We have asked big questions. Where did we come from? Are we alone? To help answer these, we build amazing tools. The James Webb Space Telescope, or Jwst, is one such tool. It is humanity's most powerful eye on the universe. It orbits the Sun far from Earth, about 1 million miles away. This special place helps it see clearly. Jwst is an incredible piece of engineering. Its main mirror is huge, over 21 feet wide. This mirror is made of 18 golden segments. Gold is very good at reflecting infrared light. Infrared light can travel through dust and gas. This allows Webb to see things Hubble could not. It can peer into stellar nurseries where stars are born. It can also look back in time to the very first galaxies. The mission of the Jwst is to explore every phase of cosmic history. It seeks light from the first stars and galaxies. It studies how galaxies evolve over time. It looks at how stars and planetary systems form. And yes, it even searches for signs of life on distant exoplanets. The telescope is a testament to human curiosity. It shows our deep desire to understand our place in the universe. The Jwst is not just a telescope, it is a beacon of discovery. Now, let's talk about a giant of science, Albert Einstein. Over a century ago, he gave us a new way to understand gravity. He called it the theory of general relativity. It describes how gravity works in the universe. It is not just a simple pull, as Newton thought. Einstein showed us that gravity is about the shape of space and time itself. Imagine space-time as a giant, stretchy fabric, like a trampoline. Now place a bowling ball in the middle of this trampoline. The fabric curves, it dips down. This is what massive objects like stars and planets do to space-time. They warp it. They create a curve. Now, if you roll a marble nearby, it will not travel in a straight line. It will curve inwards towards the bowling ball. This curve is what we feel as gravity. Einstein's theory has been tested many times, and it has passed with flying colours. It correctly predicts the orbit of Mercury. It explains why light bends around massive objects, a phenomenon called gravitational lensing. The James Webb Space Telescope peers back to the dawn of time. It sees light from the universe's infancy. Recently, in early 2025, Jwst made a very interesting observation. It was looking at some of the very first galaxies. These galaxies are incredibly far away. Their light has travelled for over 13 billion years to reach us. What Webb found there was a little unexpected. Scientists were studying how light from even more distant objects bent around these early galaxies. This is gravitational lensing. General relativity predicts exactly how this light should bend. It depends on the mass of the galaxy doing the lensing. For the most part, observations match these predictions beautifully. But in this specific set of observations of extremely distant early galaxies, something was slightly different. The patterns of light seemed to bend a tiny bit more than expected. This was not a wild deviation, but it was a consistent pattern across several of these ancient galaxies. The lensing effect appeared slightly stronger than our current models would suggest. This puzzling observation has scientists intrigued. It is like finding an ancient clue that might lead to a deeper understanding. Ripples in space-time, where the data diverges. So, what does this extra bending of light mean? According to Einstein's general relativity, the amount of bending tells us about the mass creating the gravity. If the light is bending more, it could mean there is more mass in these early galaxies than we thought. Perhaps these galaxies formed faster or grew bigger than our current models predict. Or it could mean that dark matter is clumped differently in the early cosmos. Another possibility is that gravity itself might behave a little differently under extreme conditions. The early universe was a very different place. It was hotter and denser. Perhaps general relativity needs a tiny adjustment when we look at gravity working over vast cosmic distances in such an ancient environment. This would be a profound discovery. It would not mean Einstein was wrong, but that his theory might be incomplete. Science is a careful process. These are early findings. Researchers are double-checking everything. The scientific community is now working hard to verify these results. New questions for the cosmos, rethinking our universe. If these findings are confirmed, they could have big implications. Our understanding of the universe might need some updates. It could change our models of how the first galaxies formed. This would mean rewriting the early chapters of cosmic history. It could also affect our understanding of dark matter and dark energy. New questions lead to new discoveries. The path forward: science in the face of mystery. So what happens next? The first step is always more observation. Scientists around the world will use the Jwst and other telescopes to study more early galaxies. They will try to confirm if this stronger-than-expected lensing is a common feature. They will look for it in different regions of the early universe. They will gather more data. This is crucial to ensure the observation is real and not just a statistical fluke or an instrumental effect. At the same time, theorists will get to work. They will explore different explanations. Could our models of dark matter distribution in early galaxies be improved? Are there new properties of dark matter we haven't considered? Or if the data continues to point towards a modification of gravity, they will start to develop new theoretical frameworks. These new theories would need to explain all the existing successes of general relativity and also explain this new anomaly. This process of verification and theory building takes time. It requires collaboration. It involves debates and discussions. This is the healthy functioning of the scientific method. An ever-expanding journey. The future of discovery. The universe has a way of keeping us humble. Just when we think we have a good grasp of things, it throws us a new puzzle. This potential new insight from the James Webb Space Telescope is a perfect example. It reminds us that our cosmic journey of discovery is far from over. Each new telescope, each new observation opens up new vistas, and with them new questions. This is the heart of science. It is not about having all the answers. It is about asking better questions. It is about the relentless pursuit of understanding. Even if Einstein's theory needs a slight adjustment for these extreme early universe conditions, it does not diminish his genius. It builds upon it. It shows that science is a living, evolving body of knowledge. It self-corrects. It refines. It grows stronger with each new challenge. The future of cosmic discoveries is bright. With instruments like Jwst and those yet to come, we will continue to peel back the layers of cosmic mystery. The journey continues.